All right, lesson 18 as we march on in Math 140. Uh, we turn the corner here. We are done. We've looked at whole numbers. We're done. We've looked at integers. We're done. So the next logical step is to look at fractions. So there is a worksheet in Canvas, a PDF that has these fraction bars, and you can print as many of those as you have ink to print, and you can make your own little fraction strips. Um, it's pretty straightforward that this is called a half because it takes two of them. It takes two to make a thing go right. It takes two of them to make a whole. That's the idea. Two of them make a whole, so each of them is a half. That's the idea. These are fraction strips. They are excellent for small people to understand. Oh, look, that's one. One, two, three, four. Four of these make up the same one, so each of those is 1/4. They are concrete tools that young people can use to understand fractions. Some things to consider at the start. Why is a third called a third? Go ahead. Think about that. Hit the pause button. Write it down. See if you can think about why a third is called a third. Why? Looks like if you have three of them, right? Right? If you have three of them, that makes up a whole. Why is 1/3 called 1/3? That's why. And you can explain that to a small child. You can explain that to a small child. Why is 1/5 called 1/5? Why is 1/8 called 1/8? You can explain that in a way that an 8-year-old can understand. So hit the pause button. Think about how you can model 2/5 or 3/8. Go ahead. Hit the pause button. Think about how you model that. So what did you end up doing? 2/5, 3/8. Here's 2/5. Right? Is that what you did? I'm hoping so. 3/8. Is this what you did? I am so meticulous about that. Is that what you did? By the way, which is bigger, 2/5 or 3/8? It appears that 2/5 is bigger. We're not quite sure exactly how to know that right now. It appears that 2/5 is bigger because the strip is longer for 2/5 than it is for 3/8. But we don't know yet. There isn't a good way for us to compare except by size. So how can we model that two fractions are equivalent? Hit the pause button. Take two fractions that you know are equivalent and show that they are equivalent in a way that a small child will understand. I picked 1/4 and 3/12. I picked 1/4 and 3/12. Boy, is that an utter disaster, right? Because that's not what that's supposed to do, right? It's supposed to look like this, right? It's supposed to be that they're the same, right? Like, what went wrong? What went wrong? Does it appear from this sheet that 1/4 and 3/12 are the same? Well, there's the end of 1/4, and there's the end of 3/12. So it is certain that I have just royally botched that up, and it really should be this, that 1/4 and 3/12 are the same. Hopefully you picked two fractions that you believe are equivalent. Let's see if I can screw this up twice in the same video. This is how we lose subscribers. 1/5 should be the same as 2/10. Oh, this is also going to be a disaster. Watch this go badly. Yep. Right? It's supposed to be 1/5 and 2/10. And I bet you if you go back here and you find there's 1/5, there's 2/10, they should be the same. Well, that's the way it's supposed to look. And if you printed and cut, then yours went better than mine. Let's hear it for technology. So how do we know if two fractions are equal? Are 12/20ths and 21/35ths equal? How can we possibly know that? And why did the nerd ask us to do this before the nerd asked us to do this? Think about that. Hit the pause button. How do we know if two fractions are equal? Yeah, that's a doozy of a question, isn't it? Because you're thinking about, well, can we reduce this? Can we reduce this? Because you're thinking about all the stuff that you're familiar with from when you were young. But let's think about what we've been bringing our students to understand. If we want to know if these two fractions are equal, we've got to take a look at those and make sure that they match somehow, right? We had to find a way to okay, this 1/4 is the same as those 3/12. This 1/5 is the same as those 2/10. So somehow we've got to find a way to standardize 20 and 35. And so this is where we draw on an idea we know from before, the least common multiple of 20 and 35. So what is that? Well, we remember that 20 is 2 squared times 5. And we remember that 35 is 5 times 7. And when we're looking to build the least common multiple, we take the highest power that we see for every conceivable prime factor. And so the least common multiple is 140. So 12/20ths is the same as some number of 140ths, and 21/35ths is the same as some number of 140ths. But what? And how do we know? Well, if we were to have fraction strips with 20ths, and then we were to have fraction strips with 140, it would take 7 of these to make one of those. It would take 7 of these little guys to make up one of these 20ths. So there are 7 times as many of our strips. Similarly, if we had fraction strips that were 35s and fraction strips that were 140s, there would be 4 times as many of these to make one of those. And so there are 4 times as many of those. Oh, they are the same. Those two fractions are equivalent because when we express them with the same denominator, they have the same numerator. Could we have known that before? Well, sure. We could have reduced the fractions, which is a process that we're familiar with from when we were children. So let's see if we can remember the idea of reducing a fraction to lowest terms. So 12 and 20 have a common factor. They have a common factor of 4. And so we can divide by 4 here and divide by 4 here. 12/20 is the same as 3/5. Now, why does that make sense? Well, if we were to have little fraction strips that were 1/5 each, and we were to have little fraction strips that were 1/20 each, because 20 is 4 times as big as 5, it takes 4 times as many of these to equal one of those. It takes 4 times as many 1/20ths to equal 1/5. So if it takes 4 times as many of these to equal one of those, it takes 4 times as many of these to equal one of those. So it would take 12 little pieces to equal 3 big pieces. So, this is a scaling down. We would explain this to children as a scaling down. 12/20 scales down to 3/5. The proportion is the same, but the numbers we use to express the proportion go down. Similarly, 21/35, they have a common factor of 7, so we can divide by 7, we can divide by 7, and that's the same 3/5. Again, the thing I want to drive home for us, the thing I need to drive home for us, when you were a child, you might have learned, so we divide by 4 on top and bottom, because whatever you do on top, you have to do on the bottom, or some variation on that. But that's terrible learning. We don't just parrot back a rule, oh, you have to do the same thing in both places, because we have a reason why we do that. Here we're comparing sizes of pieces. The pieces over here are 4 times as big as the pieces over here. So it takes 4 times as many things here to generate the same result. There's a reason why we do that, and it's beyond, well, you have to keep the balance. Yes, we have to keep the balance, but there's a reason why we have to keep the balance, and that's the thing you should know if you're teaching small people. Let's ask that question. Which is bigger, 1/3 or 1/4? Which is bigger? Do you have an idea? Do you have an idea? Right? You have an idea? It appears that 1/3 is bigger. Right? It appears that way. Now, it also appeared that my 1/5 and my 2/10 didn't match up, so maybe it's just that my picture is bad. Is there a way we can compare them? Sure there is. This 1/3 and this 1/4 we can express with a common denominator. Well, what's a good common denominator? What's a least common multiple for 3 and 4? The least common multiple for 3 and 4, that's 12. And so in the same way, the pieces are 4 times, let's try this again. These pieces are 4 times as big as those pieces, So it takes 4 times as many of these to equal one of those. 1/3 is 4/12. It's not just, oh, you multiply by 4, you multiply by 4, and that's why. It's these pieces are smaller than those pieces. Those pieces are 4 times as big as these pieces, so it takes 4 times as many of these to equal one of those. In a similar way, what's up top here? Right. And so which one's bigger? Well, this one's bigger. That's not a tremendous surprise to us if we're comparing, if we're taking the same whole, the same one, the same unit, and we break one of the units into 3 pieces and one of the units into 4 pieces, well, if you're only breaking into 3 pieces, that's bigger. This makes sense. Which is bigger? It sure appears that the 3/5 is bigger, right? Does that make sense? Sure it does. If the denominators are the same, then we can just look at the numerators to tell which is bigger. Just like on this slide, when the denominators were the same, we were able to look at the numerators to see which was bigger. So which is bigger? Oh, really? Almost got that wrong. 3/5 is bigger. 3/5 is bigger. This is the longer of the strips, and so 3/5 is bigger than 2/5. Which is bigger? That's a tougher go. And we don't have a 1/7 strip. So what can we do? Hit the pause button. Think about what you can do to figure out which fraction is bigger. If we're going to compare them, we need a smaller kind of strip that can relate to the 7 and also to the 9. We don't care if they can relate to the 3 and the 4. We care that they can relate to the 7 and the 9. We're going to break the 1/7 strip into smaller strips and the 1/9 strip into smaller strips. So we need a number that 7 goes into, that 9 also goes into. And I think the smallest one that does the job is 63. So we ask ourselves, these pieces have 1/9 the length. So we need 9 times more of them to make the same number. These pieces are 1/7 the size, so we need 7 times as many of them to make the same length. Which is bigger? That's bigger. So the super big takeaway from all of this, the super big takeaway, when we're comparing fractions, we need the denominators to be the same. We can compare, we compare if the numerators are the same. I mean, that, I suppose that's fine. We can compare fractions if the numerators are the same. We did that a couple of slides ago. If the numerators are the same, we can compare the fractions. We look at whichever denominator is smaller. I think it is more natural for a child to make the denominators the same. If the denominators are the same, then whichever strip is longer, well, that's pretty clear. We make the denominators the same. Whichever strip is longer, that only goes 27. This goes 28. This one is the bigger one. So 4/9 is bigger than 3/7. Okay? In the privacy of your own home, which is probably where you are right now, take a piece of paper. Take any piece of paper. That piece of paper is 2/3 of some whole. I want you to model what 1/6 of that same whole would be. Hit the pause button. Take a piece of paper. That piece of paper, let's see, let's draw. That piece of paper is 2/3 of some whole. This is 2/3 of some whole. I want you to model what 1/6 of that same whole would be. Hit the pause button. Do it. What's interesting about this, if you did it, is that you probably folded it so that you could say, okay, this part is 1/3 and this part is 1/3, which means that you're missing some other 1/3. This is the whole. So where's 1/6 of that same whole? Where is 1/6? Well, I got 3 easy pieces here, so if we just fold again, I've got 1, 2, 3, 4, 5, 6 pieces. This is one of those 6 pieces. This right here is 1/6 of the whole. It's an interesting question for you to consider, and I'm glad that you did it. All right. That's all I have in this video. You have gone way beyond what I anticipated you going beyond. Thanks for watching all the way to the end. Don't be afraid to email with questions, call with questions, jump on the Hangout with questions in a virtual office hour. All right. Be well. Hope to see you soon.